Okay, so I'm going to talk about quantum spins. So here the word quantum is very important. And restricted geometries means simply that we'll deal with chains, ladders, things, objects you are familiar with. If you want to see more on the activity of my group in this domain, you have the web page here. And these are, of course, the funding agencies that helped us eat during the various works that I will present to you. First, before entering in the work per se, I should say, I should present to you the people who actually did the work. So this line of work stems from old papers done in collaboration with Chitra and Alexei Zvelik. And more recently, at the University of Geneva, we have restarted and reactivated this line of work. And all these works are done in collaboration with Corinna Collat, who is at Bonn University. And there are various people who have been involved: Pierre Bouillot, Shunsuke Furuya, Emmanuel Ekoira. There are many other theorists here. There are too many for me to list them individually, but I want to also emphasize that we had the chance to collaborate with exceptional experimental groups, and I will show mostly 3 of them because I will present their work in this talk. It's Claude Berthier in Grenoble, Christian Rueg at PSI, and André Zeludev. I'm sure I'm not pronouncing it correctly. Oleg, you will correct me, in ETH. Okay. There is also, Christian will confirm it, the Los Alamos group with whom we had many discussions and collaborations. Okay, so what is the idea of quantum magnetism? I think this is all well known. We know that if there is enough repulsion between charge in solids, then the charge is frozen. One gets 1 particle per site. Here you can say the red dot is a spin up, the green dot is a spin down, and the charge is essentially blocked. It's called a Mott insulator. Only the spin 1/2 remains, but of course it doesn't mean that the system becomes a vegetable, because there are virtual hops that can take place, and then the spin can exchange. And this is something which was understood long time ago, that there is something called super exchange, which is not a dipolar or origin, but comes from the kinetic energy of the electrons, and which at the end gives Hamiltonians for the spins which are of the Heisenberg form. And of course I say of the Heisenberg form because you can have anisotropies, you can have additional terms. We heard yesterday and the day before about Dialoginski-Moria interactions, and so on and so forth. So here, for simplicity, I've just put the Heisenberg, but this is simply a spin-spin interaction. So I can completely ignore the charge and focus on the spin degrees of freedom. So this is something which is already very interesting, because as soon as you deal in condensed matter with charges, you have a very unknown quantities to deal with. Charges are partly screened with screening which depends on the frequency, which depends on a lot of factors, and it's in general extremely difficult to precisely estimate Hamiltonians which contain charges. We make models like the Hubble model or whatever, but these are really caricature of the reality. When we deal with a Mott insulator, when we deal with a spin, usually these exchanges are relatively short range. There are relatively few of them, so we can determine the Hamiltonian usually very precisely. And I think some of the talks we heard in the first 2 days are an example of that. There was the point in computing these exchanges very precisely. You will see that this is the same in solids, in bulk solids. Usually we know this Hamiltonian pretty well, or at least after a while we know this Hamiltonian pretty well. And that's something which is important to note, because it will be useful for what I will say later. Contrarily to systems which involve charge, where we don't know the Hamiltonian very well, in that case, we know what we start from. Then, of course, that's where the difficulty starts. So this is an interesting field. It has a remarkable physics in itself. I will present some of it. Oleg will do it. Frederick will do it also. There will certainly be other talks on this. But here I would like also to emphasize that these quantum magnets have another use, and I will try to insist on this. The remarkable physics in itself is obvious, but the other aspect might be a little bit less obvious, is that one can use quantum spin systems as quantum simulators. Now, the idea of a quantum simulator is something that, again, can be traced to some extent back to Feynman. And what is a quantum simulator? Very often, theorists use model systems. And these model systems are usually the caricature of some reality. For example, we want to explain high TC, and some people say, oh, if you solve the two-dimensional Hubbard model, you will get the solution of high TC. Of course, nobody can solve the two-dimensional Hubbard model, so then makes a lot of approximations, finds superconductivity, and then says, haha, this is the solution of high TC. But you never know if it's not an artifact of the approximation you've made. So you would like an experimental situation, which is the exact or as exact that can be realization of one of your desired model, like Heisenberg model, Hubbard model, all this caricature, Bose Hubbard model, and so on and so forth. And if you have such a system, then you just do the experiment, you measure, and you get the analytic solution, the solution of your model, without having to do a numerical simulation or without having to do a complicated analytical theory. So people have been hunting for quantum simulators, and it's not so easy because usually the models that people take are, again, simple model with only short-range interactions and so on and so forth. So it's difficult to find such systems, and essentially there are two fields which have provided easily such quantum simulators. One, I'm sure you heard about it a lot, it's cold atoms. So cold atoms have been a big help to condensed matter for the following reasons. Atoms are neutral. You can trap them in optical lattices, so in lattices which are made of light, and therefore you can realize a tight binding model of particles where the particles can hop from one minimum of the optical lattice to another, so realizing a tight binding model. Now you can wonder why there is a J here, which is normally the magnetic exchange. It's because, unfortunately, when you get two decoupled community, they don't use the same notations. And for the cold atom community, J is the kinetic energy. It's what we call T. And when we ask them why they didn't choose T, they said, but T is the time. Why should we choose T for the kinetic energy? Okay, so it caused a lot of confusion, but essentially you see that here you have particle hopping with a kinetic energy. They are neutral, so they can only see each other when they are in the same well of the potential, and you have an essentially perfect realization of what is known as the Hubbard model. So one can use these cold atoms. Of course, in reality, it looks like this. It looks like this if you take an image of the particle in such optical lattice. But you can hope that by doing such an experiment, you will get answers on an idealized model. So cold atoms was a very efficient source of quantum simulators. Now, I want to show you that actually magnetic insulators, quantum spins, can also be used in addition to their own intrinsic beauty and physics to be a source of quantum simulators. So the idea is very old. Let me, much older than this, it goes back to Holstein and Primakov and Matsubara and Matsuda. And the idea is that spins can be related to bosons. So let me give you a slightly twisted version, which involves dimer, and indeed it goes back to this paper in particular with Alexei Zvelik. So imagine I have a lattice which is made of strong bonds with an antiferromagnetic coupling here, and that all the other bonds are zero for the moment. Then it's a very simple problem. I have coverage by dimers, and you know that two spin 1/2 which are coupled have eigenstates which are either a singlet with zero magnetic moment or a triply degenerate triplet with a magnetic moment S = 1, and which can point out up in the plane or down. So this is all nice and fine, and this is a trivial ground state, But now what I can do, I can put a magnetic field. If I put a magnetic field, the singlet is insensitive to the magnetic field. One of the triplet will go down in energy because of Zeeman coupling, one will not be affected, and one will go up. So you immediately see that you will get a quantum phase transition here, something which can happen at t equals 0, when the triplet energy will go below the singlet energy. So you will go from a situation which is totally non-magnetized to a situation which is magnetized if you have put triplets inside the system. Now, of course, it's not the end of the story if you have other magnetic exchange here, because then the triplet which is on this rung can hop on the next rung using the magnetic exchange. So actually, this energy level, which here would be n-time degenerate, is now acquiring a width which is coming from the hopping acquired by the other exchange, which I call J. Now you will tell me, okay, where are bosons here, or what is the connection? Well, you see, as I think someone said, I forgot, every time I get two states, it's a spin 1/2. Well, you can say that. So here, the singlet and the lowest triplet can be viewed as a fake spin 1/2, and spin 1/2s are bosons. You can say that when the spin is down, there is no boson on the site. When the spin is up, there is one boson on the site. And this was worked out by Matsubara and Matsuda a long time ago. So here we can use this mapping. When there is a singlet here, there is no boson, let's say, no fake boson. When there is a triplet, we get one boson. Of course, you have to stop there. So you have to put an infinite repulsion between the bosons. So you cannot put two bosons on the same site, because it would have no meaning in this mapping. So this is what people call hardcore bosons. So a quantum magnet, either of dimers or of real spins, can be mapped onto a system of itinerant bosons. Because if the triplet can jump, it means that the boson here has jumped to the next site. So we can use this mapping to study indeed a system of itinerant bosons. And as I said, because of the kinetic energy of the bosons, this level here has a width. So actually you get two quantum phase transition, one when the first boson enters the system, usually at k equals 0, and then you start filling a band of these bosons, and by that point here, you have completely filled the band, and you get one boson per site. So I can map a quantum magnet system onto a model of itinerant boson on a lattice, where the xy component of the exchange is the kinetic energy of the bosons. The jz component of the exchange is the nearest neighbor repulsion between the bosons. And of course, there is also an infinite on-site repulsion to get hardcore bosons. And now you see that you have a fantastic quantum simulator for itinerant bosons. Bosons are not so easy to obtain in condensed matter. You have Cooper pairs, you have Josephson junctions, but it's still very difficult. Here, you get bosons, and not only you get bosons, but the magnetic field is a chemical potential for the bosons. So by increasing the magnetic field, I can dope my system of bosons. I can change the density of bosons, and you can do this in 3D, and with a doping possibility which goes from 0 boson per site to 1 boson per site. So empty band to filled band. We are very far from the 10% that people try desperately to realize with real particles by using gate voltage, and which is in addition restricted to 2D. So here, by twisting the problem and making it in another physical system, you see that we can really get a serious control on the physical property of the problem and go from an empty band of bosons to a filled band of bosons. In addition, as I said, the exchange are usually relatively short range and well known, so we really realize a model here which is a tight binding model of bosons in a very precise way. In addition, we have a lot of probes for magnetism. It's a field which has known a long evolution. So if I want to know the number of bosons, I just measure the magnetization, and it gives me the number of bosons. If I want to probe physical quantities for the bosons, like the superfluid correlation function or the density correlation function, I can access it via neutron scattering experiment, nuclear magnetic resonance, electronic spin resonance, and so on and so forth. So you can make a mapping, you can use this mapping. The SZ correlation function is nothing but the density correlation for the bosons, and the S- correlation for the spins is nothing than the psi dagger correlation for the boson, so the single particle correlation, which tells you if the bosons are superfluid or not. So by using this mapping, you see that you can solve something which is a fake problem of bosons by something which is a real problem of spins. And of course, that brings us close to the community of atoms, which I'm sure it's a long way to go. But if one can manufacture by atom the idealized system of spins, we can address a certain number of problems that are difficult, of course, to obtain in bulk solids by realizing spin systems. So I'll come to that. So if I look, for example, of the aspects between cold atoms and the spin systems, they are complementary. In a sense, if you look at cold atoms, you get a perfect control of the lattice and parameters. You use lasers to create your lattice, so you can get whatever you want, essentially square, triangle, blah, blah. You have perfect short-range interactions, but they suffer from inhomogeneities because they are trapped. So there is a parabolic potential keeping the atoms in place. And they have a certain number of probes to develop. This is a young field, so they are doing it very efficiently and very well. But there are still the difficulty of probing certain correlations. If you take the quantum spins, they are perfectly homogeneous, excellent. You have a perfect density control on the bosons. You have excellent probes, but of course, you have to take what your chemist friend, assuming you have a chemist friend, gives you. So, well, you know. So if you want this fantastic chain with an exchange J of this value and that, you go to see the chemist and he tells you, sorry, I have only three-dimensional materials with a J which is 100 times larger than what you want. And then if J is 100 times larger, you cannot control anything with magnetic field because you would need to apply magnetic field of 200 or 300 Tesla. So you need to find materials which are in the perfect range for what you want. And fortunately, chemists made fantastic realization in that. But of course, it doesn't replace the flexibility to be able to assemble by hand spins and atoms the way one would like it. Okay, so let me essentially show you two examples in these two fields. One is the cold atoms, but I will go very briefly on that. The second will be mostly the spin system of how one can use one of the realization to study the other problem. So with cold atoms, bosons are natural, spins are not. So let's use bosonic realization in cold atoms to study a spin problem. And I will show you then how we can use the spin to tackle an interesting, hopefully, condensed matter problem. So let me show you what people in cold atom did. They studied the propagation of a magnon. So they realized the lattice of bosons where essentially the boson carry an internal degree of freedom. Let's call them spin-up bosons. Okay? So these are the yellow bosons here. Then you change one of these bosons into a green boson, which is a spin-down. So what I have realized here is a ferromagnetic chain of particle with one spin flip. And if I have sufficient repulsion between the particle, the boson will be in a Mott insulator phase. So I will get super exchange. So this system is described by an Heisenberg Hamiltonian. And what I have realized is a nice ferromagnet with one magnon, with one spin down. It's textbook, it's in Feynman's book on statistical physics. And now I would like to know how this magnon propagates. And of course, because it's a one particle problem, we can solve it relatively easily. And when you do that, so the way they do it, they slightly lower the lattice so that now the exchange is going up because the kinetic energy is increasing, and then they follow the rays. They follow this guy because they can image the whole system and tell you exactly where this guy is located. So I won't spend too much time on this. This is something that was done in the group of Emmanuel Brock and Stefan Kur in Munich. And we helped a little bit with Thierry. Adrien Cantillon, who is now in Stockholm, is the person who is the driving force behind the theoretical analysis. There is more in this paper than what I'm telling you, but I just want to show the curve which are relevant for what I'm going to tell here. So you get the spin down at site 0, at time 0, and then you let go, and here is the time at which the measurements were done. And you very well see that the magnon is propagating. And you see also it's a quantum particle, not a classical particle, because you see the characteristic interference pattern that you would get by superimposing all the trajectories that the magnon can have. Because, of course, when you do the quantum average, the way they do the quantum average is by repeating the experiment many times. So you might have an experiment where it goes on the right, you might have an experiment where it goes on the left, but you have also a lot of other trajectories where it goes back to the center and so on. So when you do the average, you see this interference pattern. So this is doing in real space and time what neutron scattering would do in Q and frequency space. Of course, because you have a real space-time probe, you have access to certain things that would be incredibly difficult to measure using, first, there is no neutron in cold atoms. I mean, you cannot use this technique, although there are replacements. But here you can follow essentially the trajectory. You can also study, and I will not discuss it, what happens if you lower the barrier so that you're not in the Mott state anymore, and then the impurity is moving in a superfluid. Okay, I think the atoms essentially offer similar possibilities because you have the real space structure accessible. You can probe each one of the sites, so one has to think what could be the equivalent advantages that one would have in such system. But okay, the bulk of what I want to say today is directly with quantum spins. So there are many directions that people have followed. Here I will concentrate on the quantum spins under magnetic field, the one I presented. There are of course many directions, frustration and so on. But here, if you look at these systems which are in a way perfect realization of bosons on a lattice, then of course if you have bosons, the first thing that comes to mind is Bose-Einstein condensation. And yes, one can realize Bose-Einstein condensation using quantum magnets and study Bose-Einstein condensation using quantum magnets. I will not have time to discuss on this, so I refer you to two reviews which are on the market, one that we wrote together with Christian Ruegg and Oleg Chernyshov, and a more recent one from the Los Alamos group. Christian is one of the authors, Vivian Zapp and collaborators, which was published in Review of Modern Physics. Again, you have spins. These spins can be mapped to bosons, so you can ask yourself, can I have the equivalent of a Bose-Einstein condensation? And the answer is, of course, yes. Here, I will focus on another aspect, which is if I could realize spins in d equal 1, if I could realize spins in chains or ladders, I would be able to study a one-dimensional fluid of bosons. And now, of course, we start having a lot of questions and problems because we know that in one dimension, no true long-range order is possible if you break a symmetry, a continuous symmetry. So in a way, 1D bosons should not have a true Bose-Einstein condensation. And then the question is what replaces this thing, and can one study these physical properties? And the answer is yes. There is in 1D a whole set of unusual properties which go by the denomination of Tomonaga-Luttinger liquids, sometimes Luttinger liquids. And essentially, I will show you how quantum spins in one dimension help to explain these type of property. Okay, so let me move to this particular topic. Now, first, how can I get a one-dimensional system of spins? What does it mean? Because I'm talking about bulk crystals. I'm not talking about a chain of atoms deposited on the surface. So how can I do 1D? Well, for example, if I take the dimers that I was mentioning before, the reason why I focus on dimers rather than isolated spins is a little bit specialized. I don't want to discuss it here, but essentially the dimers have the advantage that for most of the phase diagram, the magnetic moment is relatively small. So parasitic interactions like dipolar forces and so on are much weaker than if you deal with normal spins. Okay, anyway, so here I have the strongest bond, for example, along my dimer. Now I can make a second bond here, which is the second strong system. And then if I have an extremely weak or even zero here bond, I will realize a crystal which is a bulk crystal where I get many chains like this. These are called ladders actually because they are made of two chains. And although the crystal will be bulk, the physical properties of the spins will be the one of a one-dimensional structure. So that's the way one can do it. One just needs to find a material in which there is a proper hierarchy of coupling. So these two couplings, okay, in the example I show here, the yellow coupling is the strongest, but it doesn't need to be so. So I have these ladders which are separated by essentially an extremely small exchange. And then I realize a one-dimensional physics. Okay, so if I take this, as I said, in 1D there is no Bose-Einstein condensation. And actually in 1D, if I think about these spins as bosons, they are hardcore bosons. As I said, you cannot put two bosons on the same side. Well, if you think about it, you're in 1D and you have a hardcore constraint, it means the boson cannot cross at all. And then they sound terribly similar to fermions. Of course, it's not exactly fermions because they are bosons and they commute, they don't anti-commute. But in a way, for their density, you get a zero of density every time you try to put two particles on the same side. So it sounds like the properties of fermions. And actually, in one dimension, you can show using a mapping which is called Jordan-Wigner transformation, you can show that you can map exactly a system of 1D bosons onto a system of 1D spinless fermions. So I recommend for you to think in terms of fermions. It's a more easy way to visualize a 1D system of hardcore bosons than to think in terms of nearly free fermions, nearly free bosons. So as I said, there is no Bose-Einstein condensation of these poor bosons here, but there is something which goes by the name of Tomonaga-Luttinger liquid, which is for interacting particle in one dimension, the replacement of what is the Fermi liquid for interacting quantum particle in 3D, let's say. So this physics is now well documented, and the question is, can we observe it in this material? So what are these properties of the Tomonaga-Luttinger liquid? The first one is that all the excitations are collective excitations. This is a particularity of 1D. If I am in 1D, imagine a line of people. Imagine we are waiting for the lunch at the restaurant, and you want to be an individual. Well, you can't. If you want to move forward, you have to push the person in front of you, which push the person in front, and push. So every motion is a collective motion. You can only have a density wave of particle that will progress, not an individual excitation. Okay? So the good excitations are collective excitation. They are sound waves which are characterized by a velocity u. Then all the physical properties are essentially power law correlations, which depends, and that's the remarkable fact, which depend on a single parameter. You can measure the density-density correlation. You can measure the single particle correlation. You can measure an horribly complicated correlation. They will, of course, behave differently, but all can be traced to a single parameter k. So let me show you an example, and this is something that was really understood by Duncan Haldane at the, let's say, beginning of the 80s. For example, if I take bosons, I can measure the single particle bosonic correlation. It decays as a power law of the distance with an exponent which is 1 over 2k. If I measure the density-density correlation of the bosons, then there are various decays, but one of them is again an oscillating component with a power law which depends in a different way than the single particle, but which again has its exponent that can be traced to the same number k. So in a way, if I know these two parameters, u and k, I can determine all the physical properties of the one-dimensional system. So this is a remarkable fact. I could write more complicated correlations. The exponent could be, I don't know, k plus 1 over k, or k plus 2 over k, or whatever. But every time this exponent is related to this single parameter k. So these two parameters are called the Luttinger parameters, and they sort of characterize practically completely the physics of 1D. So can this be measured? Of course, as you can imagine, this is a very tantalizing theory, so people have tried to measure it in many, many other systems. So there are many observations of power laws in 1D systems. For example, in organic superconductors, so-called Beshgard salts, people measured the optical conductivity, and if you look at the optical conductivity as a function of the frequency, it shows a very beautiful power law over more, let's say, 1 decade or so, which is the maximum regime you have between the bandwidth of the material and the formation of a gap in this material. So this is strong indication that this material obey Luttinger liquid law. But of course here, as I was mentioning before, this is really real electrons, so we don't know precisely what is the interaction between them. It's a screen Coulomb interaction, so we see the power law, but we have no way to ab initio compute the exponent. So we can only say it's reasonable given the value of the interactions, okay? There is the nanotubes. In nanotubes, people have seen power laws in the conductance, for example, which have been interpreted. There is some debate on this interpretation, but I don't want to go into that, which have been interpreted as the manifestation of Tomonaga-Luttinger liquid physics. But here also, in nanotubes, the interaction is complicated. It's a screen Coulomb interaction again. So we observe the power law, but we cannot say if the exponent is correct or not correct. So it's difficult to rule out another phenomenon. There has been interferences between one-dimensional condensates, which have been realized on atom chips. And these interferences have been interpreted in terms of Tomonaga-Luttinger liquid. Okay, I should have changed this. This is the full counting statistics. The red is the theory, and the bars are the measurement. So this is very consistent with Tomonaga-Luttinger liquid. Just a second. Unfortunately, the interaction in these materials is extremely weak, which means you cannot differentiate this from other interpretation like Gross-Pitayevsky and so on. Yes?
Just a question, because power laws should depend on K when it's looking at it.
Yes.
How can I map this? Is there a direct way to map this, for example, into temperature or frequency?
So when you compute this correlation, for example, this is the conductivity. So it's a current-current correlation function. Instead of having the distance as a cutoff here, you will have the frequency as a cutoff. So when you work out the current-current correlation function at q equals 0 but finite frequency, you find that it's a power law of the frequency with a certain function, let's say 4k minus 5, something like this. And then if you see the power law, you can relate this to a certain value of k. Now you can then decide if the value of k is reasonable. We know that for repulsive particle, k is smaller than 1, attractive particle, k is larger than 1, and so on and so forth. So if you find a completely banana-esque value of k, then you know your interpretation is wrong. But you cannot guarantee in all these systems that interpreting these power laws in terms of Tomonaga-Luttinger liquid is the only interpretation. It's difficult to find another one, but it can exist. There was a question from Leonid.
Maybe just a clarification.
No, here it's conductivity. For this one, it's conductivity. Because it's bulk material. No, because here there is umklapp. They are commensurate materials. So what plays the role of the scattering, if you want, is the umklapp process. Now, this... Yeah, there is. There is. Here, that's why this range here is limited. If you go below in frequency, you get a gap. So if you're above the gap, then the frequency is probing the properties of a system which doesn't know, if you want, that you have a gap. So it's still given by Luttinger liquid properties. If you get too close to the gap, you get, of course, the property of a Mott insulator. Q equals 0. Q equals 0. Yeah. Well, we can discuss. I can explain to you more in detail, but it's Q equals 0. It's Q equals 0. There was another question. Yeah.
So if you measure two different correlators, they should be connected.
Yes. You're absolutely correct. So the idea is to say, let's measure more than one correlation function and cross-check this. Actually, it turns out for practical reasons to be very difficult. For nanotube, there was, in a sense. People were claiming, even for that, there was, in a sense, people did photoemission. And photoemission measures the single particle correlation. And they saw something which was compatible with the power law, and then tried to cross-correlate the K. And it more or less works, except they saw the power law on much more than the bandwidth of the material. So it's unlikely that you get Tomonaga-Luttinger liquid properties which would extend more than the bandwidth of the material. So what I mean is that, and Leonid is absolutely correct, for the nanotube there were people who also did other experiments and tried to cross-correlate the K. So it's of course what one has to do, but actually in practice it's not so easy to do, because there is usually one good quantity you can measure in this material and not 5 of them. Same thing, you would like also here to sort of vary a parameter in the system and see if you can, for example, vary the strength of the interaction or something like this, and see if you control the exponent. Then it's a proof that you really, but that's difficult. You can apply pressure. That's essentially all what you can do. And people saw an evolution. But very difficult to compute ab initio what the pressure is doing on the interaction. So I mean, you know, I strongly believe that this is Tomonaga-Luttinger liquid. Actually, I'm a co-author of this paper, so I put my chips in this paper. But I must also say that if someone comes and tell me I found an alternative explanation of this power law, it's there. I cannot completely cross-correlate the exponent with anything which is known. So again, you can say, you know, it's circumstantial evidence if you want, but it's not what I would call a smoking gun experiment. Okay, let me move a little bit forward. So as I said, the exponent is an adjustable parameter. Testing the universality is what you ask. Can I do several experiments? Can I have a control parameter, and so on and so forth? And of course, what I would try to convince you is that by using this material, this quantum spin, this puts you in a much better position. So first, let me show you that the idealized material that I showed you before, this organic ladder, it exists. Here is the structure. So the material is made of several of these ladders, which are stacked in this, so there are 2 inequivalent ladders inside the material, but the exchange are the same and so on. It's just their orientation which is different. And they, just to give you an idea of the order of the couplings, now you would say, how do you know the couplings? Well, there are 2 ways we know the couplings. We can fit them by computing physical quantities, and I'll show you that we can compute them with perfect accuracy. So we go from a model to the physical quantities without any approximation, but also they can be directly measured in neutron scattering experiments. So we know this exchange. So for this ladder, this is about 12 Kelvin. This is about 4 Kelvin, this exchange. And this exchange here between ladders is about 50 millikelvin. So for a whole range of temperature, the approximation of having independent ladders is extremely well justified. So as long as I don't go around 100 millikelvin, then I can really consider that this material is in one-dimensional situation. If I go below, I have to worry about what the third coupling will do, and what it will do is give me three-dimensional ordering of the system. Okay? So this system will have two behaviors. One behavior which is really characteristic of 1D, and if I go to too low temperature, I will get a behavior which is more characteristics of a 3D magnet. Okay, so now how can we study this problem? I showed you this bosonization, these Tomonaga-Luttinger liquid properties. They are valid asymptotically, low energy properties, long distance, large time. Now, if we study, we can use either an analytic technique, which is usually, there is one which is known as bosonization, which is extremely efficient, but this is giving asymptotic properties, low energy, large time. Or I can do numerics. If I do numerics, I'm efficient at short distance, short time. Okay? And I try to combine the best of both worlds. So what we will do, we will use the numerics in the regime where it's efficient, and we will extract the parameters, the U and the K, which allow us then to plug them in the field theory, plug them in the analytic solution, and with that we can compute the other part of the response. And if we have the chance to have an overlap between the two methods, then we can get a rather complete description of the system. And of course, what we will use is the Giamarchi method that is extremely efficient in one dimension. That is probably the best method to use in one dimension. And with that, you will see that we can get a relatively complete description. So what we do, we compute numerically using Giamarchi all these non-universal parameters, the Luttinger parameters, there is the amplitude for the fields, I don't want to go into detail, from the Hamiltonian. And we know the microscopic Hamiltonian precisely. So there is here no approximation. I mean, 10 to the minus 6 in the numerics or something like this. No, I'm joking, but it's very good. Here is, for example, for the compound I showed you, as a function of the magnetic field. So for empty band of bosons, field band of bosons, so only singlet here, fully polarized triplet here, the Luttinger parameter K, which is doing here the red curve, and the velocity U, which is also doing the red curve. Forget the green curves. They are an analytic approximation, and although it qualitatively reproduce the parameters, it doesn't reproduce them quantitatively. So the curve to look at are the red curve. So these are stupid non-universal parameters, but we can compute them with 100% accuracy. Then we inject it in the analytic solution that the Tomonaga-Luttinger liquid theory provides us. For example, here is the NMR relaxation time, the so-called 1/T1, which is given analytically by this formula, except normally you don't know what K is, you don't know what U is, and so on and so forth. Here we know. So we start from the Hamiltonian, and without any approximation, we go to this formula. And then we can compare with experiments. Okay. So let me show you the comparison with NMR experiment done in Grenoble. The dots are the NMR experiments, and the red curve is the theory where there is essentially no adjustable parameters. And you see that it fits perfectly the experiment. There is one parameter which is not so well known, which is the hyperfine coupling. So it's one number for the whole curve, which means we can sort of shift this red curve up and down. Not too much, because otherwise the experimentalists will tell us that we take completely crazy hyperfine coupling. So you see that this is a very stringent test of the Tomonaga-Luttinger liquid theory. Okay. We can even go beyond, because I told you if we go to low temperatures, then this system will order. Now we can compute the ordering temperature by doing RPA, by doing standard mean field theory. Mean field where we treat only the perpendicular coupling in mean field. And since we know the exact solution along the chains, we can do a reasonable job in computing the ordering to the 3D ordered phase. And here again, you see the dots are the NMR results, and the red line is the calculation. Here there is, of course, an adjustable parameter, which is the transverse coupling. This one is way too weak to be measured by neutrons. So, okay. Same phase diagram measured by neutrons instead of being measured by NMR, and it gives essentially the same result. So you see on this example that we have a pretty good control on the theoretical side of these quantum spin systems, and on the converse, that they can be used to answer really fundamental question. For example, does this Tomonaga-Luttinger liquid theory works quantitatively? And indeed, it works beautifully quantitatively in this type of system. Let me show you another example of weird 1D physics that one can test. In 1D, there is a fractionalization of excitations. If I consider a magnetic system with antiferromagnetic coupling, you would imagine that the minimum excitation I can do is a magnon. I can flip a spin here. I go from -1/2 to +1/2. So the excitation is a delta SZ equal 1 excitation. And in high dimension, it should behave as a particle with a well-defined energy and a well-defined momentum, if I create it with a well-defined momentum. In 1D, it doesn't work that way. If I look at this magnon excitation and I flip these two spins and I flip these two spins, you see that this magnon excitation, it splits into two excitations. So it fractionalizes, it breaks into something which one can prove is only a spin 1/2 excitation. It doesn't seem possible. It's like if I was telling you, I take one electron and I break it in 3. Well, it's possible in the fractional quantum Hall effect. Here it's the same. Because the material is 1D, you can break an individual excitation into parts which of course would not exist in another world outside the 1D world. So this magnon, if you excite it, will immediately break into two excitations which go by the name of spin-ons. And of course this has consequence. The energy of the magnon is now the sum of the energy of the two spin-ons. And the momentum of the magnon is the sum of the momenta of the two spin-ons. But there is plenty of way you can spread the momentum, and therefore the energy is also completely spread. It's not a well-defined energy momentum curve. It depends on this internal variable K1. So instead of having a nice dispersion relation for the magnon, what you have is a continuum of excitation. Here is the continuum of excitation of the energy as a function of Q that you would have. Potentially, you can get absorption in all this region. This is something known by people doing better ansatz long time ago. It's called the Descloiseau-Pearson spectrum. And it comes from the fact that there is this fractionalization of excitation, which means that if I do neutron scattering experiment, I should see this remarkable structure. And indeed, it has been observed in a variety of compounds. Let me show you how it has been observed in the ladders, but also that now we are able to compute this correlation function. So here is a calculation using directly Giamarchi of the neutron absorption spectrum, so the S+, S-, SZ, and so on correlations as a function of the momentum and the energy, and of course the color code is the intensity of the spectrum. And there it's, if you want, an ab initio calculation. We start from the Hamiltonian and we give the correlation functions. And we can compare with actual neutron scattering experiments, and you see that the agreement is, of course, truly excellent. So again, to summarize, numerics is good in short time, short size, let's say. Analytics is good in the opposite situation. So if we combine the two, we can get a complete description. And of course, this paves the way to study more complex systems. Let me just flash other examples. One example on ESR that I will not touch. So I will give you just the reference. And I'll just show you that using this possibility to get the correlation function exactly, we can even reconstruct an Hamiltonian. So here is a compound, which is called DIMP, that was studied by neutrons at PSI, and they know it's a ladder, but they didn't know the coupling constant. So what we did, we took their neutron points, and we let a calculation run with arbitrary ratio between the leg and rung coupling up to the point where we can match the experiment. And because we know that we are able to compute the correlation exactly, it means that if we match the experiment, we have the right Hamiltonian. And actually, this is a beautiful compound because it turns out to be a weak rung coupling. This time, the strongest coupling is on the legs, and the rung is a weak coupling. So this is something that one can imagine doing in more complicated situation. Let me go rapidly. Let me skip the bound state of spin-ons. And of course, now we can also use the compounds as quantum simulator for studying some open problems. The first one is dimensional crossover. I showed you this example of weakly coupled 1D structure. It only works if you're far from a quantum critical point. Here is the energy excitation of, let's say, a one-dimensional chain with a chemical potential here. If the coupling J prime to other chains is weak, then I can view this as indeed weakly coupled one-dimensional structures. But if I move close to a quantum critical point, then the chemical potential will be very close to the bottom or the top of the band. And then by definition, the coupling J prime will become larger than this. And then I'm in the unknown. I have to treat the problem as an anisotropic 3D system. And therefore, we have a very interesting dimensional crossover between a 1D structure, or weakly coupled 1D structure, and essentially 3D structure. In 3D, bosons behave as bosons. In 1D, I told you they behave as fermions, so it's a little bit like crossover. Okay, let me skip that. We can use these materials to study the effect of disorder. There is a very interesting phase, which is called the Bose glass phase, which is realized when you put bosons in a random potential. And this phase has been hunted in various situations. Well, using disordered magnets, you can do it. I'll skip on the properties of this Bose glass phase because I want to reach the conclusion. But I just want to show you that people have used these magnetic insulators to test for this, because what you need to test for this Bose glass phase is that the phase is compressible, and that you can do very easily by computing dMdh, because it's dNdh for bosons. And you can also test that it has no superfluid order parameter, because measuring the superfluid order parameter is like measuring the Sx component of the magnetization in spin systems. And there are many experiments that have been done. I flashed some of them that have been done to test whether disorder in this system, which is realized by alloying the material. Here you see an alloy where you go from a totally chlorine version of the material to a totally bromine version of the material, where you can realize this disordered system. Okay, so to conclude, I tried to show you that localized spin systems have very interesting behavior that one can connect to itinerant quantum systems, that the dimers have proven that they can be used to study this type of behavior, that one, I think, remarkable result is that they allow to test quantitatively the Tomonaga-Luttinger liquid predictions, but more interestingly, that the sky is the limit. We have on the theoretical side a pretty good handle on the correlation function, and we can now use this system to tackle really open problems. So among the perspectives I mentioned, behavior to quantum critical point, effect of dynamical quantities, and of course impurities. Now, if I wanted to finish by connecting to, in my opinion, and based on the talks I heard in the last 2 days, where would adatom have really an edge? I think it's hopeless to try to realize as many spin as the chemists can realize. But on the contrary, well, there are 10 to the 23, so you will not align them. But on the contrary, there is a fantastic control on J. You can put the atoms where you want. There are a lot of very interesting anisotropies and large couplings, such as Dialoginski-Moria, that can be realized, which would be very difficult to realize in normal materials. I think, of course, edge states have been already mentioned. I think, for example, realizing things like changing the exchange symmetrically in a chain, which is something that Jan looked long time ago. We did also some work with Boris Schreiman and Alan Clark on the subject. This is realization of two-channel Kondo problem, and practically difficult to realize in bulk materials. But of course, with atoms, maybe this is something that can be really put in the experimental bag of tools. And I think also the idea of controlling the transverse dimensions is something which is more easy to realize with atoms than with bulk materials, putting several chains together and seeing how the physics changes. So I think there is a bright future for maybe merging or putting in contact the two communities. It clearly will take time. It will clearly not be for all problems, but I'm certainly looking forward to it. And with that, I thank you for your attention.